Welcome to the 8th program on electromagnetics. Today we shall start with the third part, which is magnetostatics. So far we have discussed the vector analysis and the electrostatic fields. In magnetostatics, we will be talking about the Biot-Savart law and the Ampere's circuited law and its applications. Thereafter we will be talking about the curl and the Stokes theorem, which would be followed by magnetic flux and magnetic flux density. Thereafter we will be talking about the scalar magnetic potential and vector magnetic potential, and finally we would discuss the derivation of Biot-Savart law and Ampere's circuited law. Now, a magnetostatic field is a field that is produced by charges moving at uniform velocity or by steady currents or DC currents, and whose value at any point in space does not vary with time, that is, it is time invariant. Now, we shall talk about two vectors over here. One is H, the magnetic field intensity, and B, which is magnetic flux density. The two Maxwell's equation associated with magnetostatics are curl of H is equal to J and del dot B is equal to 0, that is divergence of magnetic flux density is equal to 0. There are two laws governing magnetostatics. First is the Biot-Savart law, and the second is a special case of the Biot-Savart law, which is the Ampere's circuited law. The table 8.1 gives the analogy between electric field and magnetic field, where a number of parameters including basic laws, force law, source element, field intensity, flux density, relationship between fields, potentials, flux, energy density and Poisson's equation are compared. Now we come to the Biot-Savart law. The Biot-Savart law states that the magnetic field intensity dH at a point P due to a current carrying element is directly proportional to IDL and sine of the angle alpha between the current element and the line joining the element to the point P, and is inversely proportional to the square of the distance r between the element and the point P. Mathematically, we can write it as dH is proportional to IDL sine alpha upon r square, and when we take the constant of proportionality, then it becomes dH is equal to k IDL sine alpha by r square, which can be written as dH is equal to IDL sine alpha upon 4 pi r square, where the constant of proportionality k is equal to 1 by 4 pi. Using the concept of cross product, the above equation can be put in the form of dH is equal to IDL cross vector r upon 4 pi r cube, where r is mod of r and unit vector AR is equal to r by r. The direction of dH can be determined either by the right hand rule or by the right hand screw rule as given in figure 8.2. Just as we have different charge configurations in electrostatics like the line charge, surface charge, volume charge, in a similar way we have different current distributions. We have the line current, the surface current and the volume current. If we define K as the surface current density, unit is ampere per meter, and J as the volume current density, whose unit is ampere per meter square, then the source elements are related as IDL is equal to KDS is equal to JdV, and they can be seen in figure 8.4. Thus, in terms of the distributed current sources, the Biot-Savart law becomes as shown in equation 8.6, 8.7 and 8.8 for the line current, surface current and volume current. The Biot-Savart law is now used to determine the field due to a straight current carrying conductor of finite length AB. We assume that the conductor is along the z-axis with its upper end and lower end subtending angles alpha 2 and alpha 1 respectively at point P, the point at which H is to be determined. If we consider the contribution dH at P due to an element dl whose coordinates are 0, 0, z, then as per Biot-Savart law, dH is equal to IDL cross r upon 4 pi r cube given by equation 8.9. But from the figure it can be seen that dl is equal to dz az and vector r is equal to rho a rho minus z a z. Therefore, dl cross r becomes equal to rho dz a phi. Putting this in equation 8.9 and taking the integration, we get the expression for h as given in equation 8.11. Now we would like to introduce alpha 1 and alpha 2 into the expression for h, and for that we make a mathematical transformation as letting z is equal to rho cot alpha, and when we differentiate it we get dz is equal to minus rho cosec square alpha d alpha, and putting this into equation 8.11 we get the value of h as given in equation 8.12, which is h is equal to I upon 4 pi rho into cos alpha 2 minus cos alpha 1 into a phi. Here h is always along the unit vector a phi, which are concentric circles, and they are irrespective of the length of the wire or the point P. As a special case, when the line conductor is semi-infinite with respect to point P, then the coordinates of point A becomes equal to 0 0 0 and that of B becomes 0 0 infinity, so that alpha 1 becomes 90 degree while alpha 2 becomes 0 degree, and under such a case h is equal to I upon 4 pi rho a phi. Again, as a special case, if we take an infinitely long conductor, then point A becomes 0 0 minus infinity while point B becomes 0 0 infinity. Under such a case, alpha 1 is equal to 180 degree while alpha 2 is equal to 0 degree. Under such a case, the value of h comes out to be I upon 2 pi rho into a phi. To find the unit vector a phi is not always easy, and for that a simple method is that a phi is equal to al cross a rho, where al is the unit vector along the direction of the current element, while a rho is a unit vector along the perpendicular line from the conductor to the field point. Next we come to the Ampere's circuit law. Here we shall also get the first Maxwell's equation in magnetostatics. The Ampere's circuit law states that the line integral of dH over the closed path is equal to the net current enclosed by that path. Mathematically, the line integral of h dot dl over the closed path is equal to I enclosed. Now applying Stokes' theorem to equation 8.16, we get equation 8.17, where the line integral has converted into a surface integral. But at the same time, I enclosed is also equal to surface integral of j dot ds. If we compare equation 8.17 and 8.18, we get curl of h is equal to j. This is nothing but the first Maxwell's law of electromagnetics. It is the point form of Ampere's circuital law, while h dot dl over the closed path equal to I enclosed is the corresponding integral form. Now it should be noted that the magnetic field is not a conservative field. Next we come to the application of Ampere's law. The Ampere's circuital law is applicable to cases where the current distribution is symmetric. The solution is easy if you are able to find a closed path known as the Amperean path, which satisfies two conditions. The first condition is h should either be everywhere normal or tangential to the closed path, so that h dot dl becomes equal to h dl or 0. And secondly, on that portion of the closed path where h dot dl is not equal to 0, h is a constant. The first condition allows us to replace the dot product by the product of the scalars, while the second condition allows us to bring h outside the integral. Now we shall take some cases to apply Ampere's law. The first is a infinite line current. Let us consider an infinite long filamentary current carrying current I along the z axis. We are required to determine h at a point P, for which we choose a closed path known as the Amperean path through P, which satisfies the two conditions just mentioned. Here that closed path is a circle with center on the z axis and passing through point P. Now since there is cylindrical symmetry, we have h is equal to h phi a phi and dl is equal to rho d phi a phi, and when we put these values in the Ampere's law, we get H phi is equal to I by 2 pi rho, and therefore H is equal to I by 2 pi rho into A phi. Now it can be seen that the amount of labor and time required to find the value of H due to an infinitely long conductor is very less as compared to when we did the same thing using the Biot-Savart law. The second condition is of an infinite current sheet which is at Z is equal to 0 plane, and where the surface current density K is pointed in the y direction, as can be seen in figure 8.7. To apply the Ampere's law, we take an Amperian path. Here it is the closed path 1, 2, 3, 4, and when we apply it to this path, we get H dot dl is equal to Ky into B. To evaluate the integral, we first need to know what H is like, and to achieve this, we regard the infinite sheet as comprising of filaments. We need to find dH above or below the sheet due to a pair of filamentary current, which can be found using the expression H is equal to I upon 2 pi rho A phi, and A phi is equal to AL cross A rho, which have already been defined earlier. From figure 8.7b, the resultant dH has only an x component, and H on one side of the sheet is opposite to that on the other side. Due to the infinite extent of the sheet can be regarded as consisting of such filamentary pairs so that the characteristics of H for a pair are the same for the infinite current sheet, that is, H is equal to H naught into Ax for Z is greater than 0, and H is equal to minus H naught Ax if Z is less than 0, where H naught is yet to be determined. Now when we apply the Ampere's circuital law to the Amperian path, we get the expression H dot dl over the complete path is equal to 2 H naught into B. But at the same time, H dot dl is equal to Ky into B. When we compare the two expressions, we get the expression for H naught, which is equal to Ky by 2. Putting this value in equation 8.22, we get the final value of H, which is equal to H is equal to half Ky into Ax for Z greater than 0 is equal to minus half Ky into Ax for Z less than 0. In general, for an infinite sheet of current density K ampere per meter, H is equal to half K cross An, where An is a unit vector directed from the current sheet to the point of interest. The third case is of an infinitely long coaxial transmission line. Let us consider an infinitely long transmission line consisting of two concentric cylinders as shown in figure 8.88. The inner cylinder or the inner conductor is of radius A and carries current I, while the outer conductor has a radius B, has a thickness of T and carries current minus I, or the return current. We are required to find H everywhere, assuming current to be uniformly distributed in both the conductors. As can be seen in figure 8.88, there are four regions. The first region is rho is between 0 and A, the second region where rho is between A and B, the third region where rho is between B and B plus T, and the fourth region is where rho is greater than or equal to B plus T. The Amperian path for the first region is L1, for the second region L2, and similarly for the third and fourth path as L3 and L4 respectively. We are required to determine H in all these four regions. For the first region, that is when rho is between 0 and A, we have the Amperian path L1, and after some manipulations we get the value of H phi as I rho upon 2 pi A square. Similarly, we can find out the H phi for the second region, which comes out to be I upon 2 pi rho. For region between B and B plus T, we get the expression of H phi as given in equation 8.29, and for the fourth region we get the expression of H phi to be equal to 0. And when we club all the four regions, we get the equation 8.31, which gives us the value of H for the entire region. The sketch of H phi versus rho is shown in figure 8.9. From A to B, the H phi varies linearly with rho. From A to B it is inversely proportional. From B to B plus T again it is inversely proportional, and for rho greater than B plus T the value is 0. Regarding curl, we had already discussed curl in the second program when we talked about the various operations of the del operator. There we had discussed the physical significance of curl, its various expressions, the various identities associated with curl, and the Stokes theorem which relates a line integral to a surface integral. Next we come to magnetic flux and magnetic flux density. The magnetic flux through a surface S is given by phi is equal to surface integral of B dot ds. Now the magnetic lines of flux are closed lines. They have no beginning nor end. The flux lines do not terminate on a magnetic charge, and therefore the Gauss's law for magnetic field is the surface integral of B dot ds over the closed surface is equal to 0. That is, an isolated magnetic charge does not exist. If we apply divergence theorem to equation 8.30, we get a volume integral, and from there we get del dot B is equal to 0. This is the second Maxwell's equation of magnetostatics, which indicates that magnetostatic fields have no sources nor sinks. Next we come to scalar magnetic potential. While studying electrostatics, it was found that the solution of the electrostatic field problems is greatly simplified by the use of electrostatic potential V. Similarly, we can define a potential associated with magnetostatic fields. In fact, the magnetic potential could be either a scalar Vm or a vector A. Just as E is equal to minus gradient of V, in a similar way H is equal to minus gradient of Vm, but with the condition that J is equal to 0. Now let us understand the significance of J is equal to 0. Now curl of gradient of any scalar is equal to 0, or curl of gradient of Vm is equal to 0, or curl of H is equal to 0, but curl of H is also equal to J, which is the first Maxwell's equation of magnetostatics. If we compare equation 8.33a and 33b, we get curl of H is equal to J is equal to 0, or we can say J is equal to 0. Thus it means that equation 8.32, that is H is equal to minus gradient of Vm, can exist only in a region where there is no current density. Also, since del dot B is equal to 0, therefore del dot H is equal to 0, or del dot minus gradient of Vm is equal to 0, or Laplacian of Vm is equal to 0 under the condition J is equal to 0. This shows that Vm continues to satisfy Laplace's equation in homogeneous magnetic materials. However, it is not defined in a region where the current density does not exist. The scalar magnetic potential Vm is useful in solving problems involving geometries where the current carrying conductor occupies a relatively small fraction of the total area of interest. The scalar potential Vm is also applicable for permanent magnets. The scalar magnetic potential is not a conservative field. Its unit is ampere. While dealing magnetic circuits, it is convenient to call Vm as magnetomotive force. When we compare V and Vm, it is found that V is a single valued function of position, while Vm is a multi-valued function of position. Next we come to vector magnetic potential denoted by A and whose unit is Weber per meter. We can define the vector magnetic potential A such that B is equal to curl of A, and we get this expression from the fact that the divergence of curl of any vector A is equal to 0, and we also have del dot B is equal to 0. If we compare the two, we get B is equal to curl of A. The vector magnetic potential is very useful in all regions irrespective of the fact whether current density exists or not. It is also applicable in the time varying case. The vector magnetic potential is very useful in studying radiations coming from apertures and antennas, and for the leakage radiations coming from transmission lines, waveguides and microwave ovens. The vector magnetic potential does not have any physical significance. However, it is a very convenient step in determining B, which is obtained from the space derivatives of A rather than A itself. Now, the vector magnetic potential can be obtained by two ways. One is by the method of analogy and the second is by using the Biot-Savart law. Going by analogy, just as we defined V is equal to integral of dq by 4 pi epsilon naught r, in a similar way we can define A, and which is given by equation 8.36a, 36b and 36c for the line current, surface current and volume current. We shall now determine A using the Biot-Savart law. Now, since B as given in equation 8.37 and using the condition given in 8.38, where the differentiation is with respect to x, y and z, we get the expression for B as given in equation 8.39. Now, we shall make use of the identity given in equation 8.40 and we will choose 1 by r as a scalar and dl prime as a vector, and we will obtain the expression for dl prime cross gradient of 1 by r. Since del operates with respect to x, y and z, while dl prime is a function of x prime, y prime and z prime, therefore del cross dl prime is equal to 0, and therefore equation 8.41 reduces to the 1 given in equation 8.42. Putting this value in equation 8.39, we get the expression of B as shown in 8.43. But B is also equal to curl of A, and comparing the two, we get the expression of A which is equal to that given in equation 8.44. Having found out A, now we can determine the flux in two different methods. First is given by equation 8.45 and the other given in equation 8.46. Also, the magnetic field intensity H can be determined either using Vm or A, just as we could determine E using Vm in the electrostatic case. Next, we come to the derivation of Biot-Savart law. The Biot-Savart law can be derived using the concept of vector magnetic potential A. The expression of A has been assumed to have been found out by analogy of the potential V in the electrostatic case. We get A as given in equation 8.47. Again, since del dot B is equal to 0 and divergence of curl of any vector A is equal to 0, therefore B is equal to curl of A, which can further be expanded as given in equation 8.48. Again, considering the identity given in equation 8.40, where 1 by r is taken as a scalar and dl prime is taken as a vector, we get an expression for curl of dl prime by r given in equation 8.49. Putting 8.49 into equation 8.48, we get the expression for B as given in equation 8.50. Again, since del operates with respect to x, y, z and dl prime is a function of x prime, y prime and z prime, therefore del cross dl prime is equal to 0. So, we come to the end of the program. In this program, we have introduced magnetostatics, where we started off with a discussion on Biot-Savart law followed by Ampere's circuit law. We talked about the curl and the Stokes theorem followed by magnetic flux and magnetic flux density. Thereafter, the concept of scalar magnetic potential and vector magnetic potentials were introduced, and finally we had the derivation of Biot-Savart law and the Ampere's circuital law. I hope you have enjoyed this program. Thank you.